IIT Kharagpur, supported by Birmingham Environment for Academic Research and National Supercomputing Mission Nodal Center for Training in HPC and AI in IIT Kharagpur. In this symposium, we will have presenters including eminent researchers and people involved with different OpenFOAM consortium activities from different parts of the world. At least 3 continents and 6 countries are participating in this symposium. We also have student presentations, and tomorrow we have 3 training sessions, 3 training cum demonstration sessions. So the Nodal Center for Training in HPC and AI is supported by National Supercomputing Mission in IIT Kharagpur. We host a supercomputer named Param Shakti, which is 1.3 petaflop supercomputer, and we have an academic unit named Center for Computational and Data Science, which hosts both the supercomputer as well as this Nodal Center for HPC and AI training. We have with us Professor Somnath, head of the Center for Computational and Data Science in IIT Kharagpur, and we also have Professor Chandan Bose from University of Birmingham, who is jointly co-coordinating this symposium along with me. I am Professor Somnath from IIT Kharagpur. So I'll request Professor Somnath to kindly give inaugural notes in this symposium. Professor De, can you hear me? Hello?
Yes, we can hear you.
No, I think he
Professor
has.
De, can you hear us?
No, he is not made a presenter. Wait a minute.
Okay.
Professor Somnath De, you can probably unmute now.
I welcome all the workshop participants on behalf of Center for Computational Data Sciences, IIT Kharagpur. I also welcome Professor Chandan Bose from Birmingham Environment for Academic Research. So thank you for agreeing to be a part of our Nodal Center initiative. So just to give a feel of the things that we do, like Somnath has already said, we have a supercomputing setup here, and we provide supercomputing services to many other institutes across Eastern India for various kinds of research activities. And among all these different research activities that we support, computational fluid dynamics is one of the important thrust areas, because there are lot of CFD researchers at IIT Kharagpur. Also, it is a great thing to have this kind of an symposium where we are promoting some software solution which is an open source infrastructure which can scale across distributed platforms. So we have a great audience here, and we also have a well-known speaker of the area. So I am just keeping it short, and I think we all will benefit from this symposium. Thank you.
Thank you, Professor De. I'll now request Professor Chandan Bose to share his notes on this symposium. Before we move forward, why is this symposium, and what will be the goal of the symposium? We'll discuss on this.
Thank you, Professor Somnath Roy. And I also thank you, Professor Somnath De, for actually allowing us to organize this event under the banner of the NSM Nodal Center for Training in HPC and AI. And then I welcome you all in this event of first UK Indian online OpenFOAM symposium, which of course is not going to be the last one. So we are just starting, and we would like to organize this kind of events in a larger scale in the coming years. Now, starting with why we thought of this event, you all know who have joined this event is that there is a exponentially growing interest in open source CFD codes, and of course making CFD codes and solvers available to everybody so that they can actually see the underlying codes and the governing equations, how we are going to solve it and use it for different applications under the broad umbrella of computational fluid dynamics. And with that in mind, we thought that we should organize something which actually can benefit broadly the students and scholars in India and UK. And we organized this from the University of Birmingham and IIT Kharagpur jointly to actually design this event as a mix of some expert talks as well as some basic fundamental trainings for the beginners in this software or in the CFD code, which is OpenFOAM. Now, why are we really interested in OpenFOAM? I normally try to start with the full form of the acronym OpenFOAM, although every one of you must know this. It is an open source CFD code of field operation and manipulation. And OpenFOAM is actually no black box. So it is a bunch of C++ codes that you can actually see it, modify it, make your own solvers, etc. And it is a very powerful tool and repository of codes that we all can use in different areas of computational fluid dynamics. And we want to promote the use of this OpenFOAM tool for our research, for learning CFD from the basics, etc., etc. So with that motive, we started this initiative. We have got a great response around, I think, around 800 to 900 registrations, and some of you have already joined. We have 200 participants strong this event. So I really hope that this event is going to be successful and useful, and we will consider that our efforts makes it worth spending the time organizing it. So with that, I just want to give some basic details of the logistics of the events. Now, as I have already told, and Professor Roy has introduced, that this event is designed to give you a feel of the ongoing research in computational fluid dynamics in OpenFOAM, using OpenFOAM, and we have invited, and many eminent researchers in the field around the world have agreed to share their ongoing research of their research group using OpenFOAM. And then we will organize a panel discussion today, which will basically talk about or discuss the theme of open source CFD coding versus the proprietary softwares or in-house codes developed in different groups, which will give us an idea of what is the future outlook of this kind of open source softwares. And then following that, we have a set of invited talks today, which will give you, again, a broader perspective of users of OpenFOAM in different areas. And tomorrow, we have the first two sessions. They are composed of the talks by the research student, PhD scholars in different institutions of UK and India. And then we have actually initially thought of having 3 fundamental training sessions, but we are fortunate that we have two more colleagues who are talking about very interesting 2 topics of post-processing using Python and using OpenFOAM in different advanced meshing like Snappy Hex Mesh. So we have 5 trainings totally tomorrow, along with the talks from the PhD scholars. So this is what this event looks like. And with that idea, I actually, before we start with the actual session, I want to thank all the speakers who have kindly agreed to my invitation and to spend their time on a Friday in this event and share their knowledge with you all. And of course, my acknowledgement goes to University of Birmingham, Birmingham Environment for Academic Research, IIT Kharagpur, NSM Nodal Center for Training in HPC and AI, and last but not the least, if you know FOSSEE project in IIT Bombay, together with FOSSEE, we are trying to make an effort to promote this kind of open source tools in India. And of course, all of you who have showed interest to join into this 2 days event and learn with us together in different perspective of OpenFOAM. So that's all I want to say. Without further ado, we want to take a little bit break before we start the actual talks as per the schedule, which has been mailed to all of you. And I just want to say that we have a large amount of audience, so we can't allow you to speak every time. So I would request you, all of you, to post your queries in the chat box, and maybe we can take few questions at the end of each session. So now I pass it over to Professor Roy before we start with the actual session.
Thank you, Professor Bose. And we'll be starting the session soon. As Professor Bose has already mentioned, there are few norms which you need to follow because we have large number of participants attending online this symposium. So we will keep everybody in the attendee mode. That means you cannot speak or you cannot turn on your video during the presentations. But if you have any question, you may raise your hand, or preferably you can write in the chat box. And depending on that, for some of the participants, chat box may not be visible, who are not using, may not be having a Teams account, chat box may not be visible to them for them. Please raise your hands and we'll take the questions as and when it is possible accordingly. Preferably we'll take the questions at the end of the session. And there we are recording all the sessions. After the symposium is over, you will get a link for the for all the recordings shared through some cloud. However, we will be, because there are a large number of participants and not all the participants attend the sessions, will share a feedback form at the end of the symposium. Only the participants who will fill up the feedback form will get a link of the videos. So please be sure that you fill up the feedback form in time, and based on the feedback response, we'll share the videos. Now we'll take 2-3 minutes break, and then we'll start our session from 2:30 p.m. Indian Standard Time. But before we move forward, if anybody has any question, you may raise your hand, and I'll make them a presenter so that they can speak out and tell the question, or you can write in the chat box also. Let me look into the chat box also. But if anybody has any other question, you can raise he or she can raise the hand. So I can see one raised hand, Jitendra Kumar Rao. If you have, I'm changing the preference for Jitendra Kumar Rao and Manikandan. If you have anything to ask, you can unmute yourself and ask the question. Jiten Kumar Rao, if you have anything, you can unmute. Or Manikandan, if you have any query, you can unmute yourself. But preferably, if you can see the chat box, you may write your concerns in the chat box, and not every time we need to listen to you, but we can, as and when the sessions are going on, we can also resolve the concerns.
Hello, sir.
Yes, I can hear you.
I am Jiten Kumar Raut from Bhubaneswar, Odisha. Completed MTech and joined very short-term course at the Indian Statistical Institute, Generative AI, Machine Learning, and completed 1 year training and workshop, and also joined at IIT Kharagpur few symposium, 5 symposium, 5 certificate already.
Yes, what is your concept?
So, sir, actually, I am also working. I would like to work in application of fluid dynamics in aerospace engineering. So I have also joined in some program.
We'll take a feedback session at the end of the symposium tomorrow, and then we can discuss about your interests and what can be the follow-up activities.
Yes, sir. I am also working in this application of fluid dynamics. Already install ANSYS software and OpenFOAM. Both are also useful in design of these aerospace related.
Nice to hear from you. I think I request all the participants, if you need to speak, please raise your concern, and at the tomorrow towards the end of the session we'll discuss all
regarding accessibility and modalities of the workshop, because we'll start the technical sessions very soon. You can get it addressed now. But regarding your follow-up activities, research interests, etc., we'll definitely have an interaction session at the end of the workshop. And there is one question regarding certificates. Yes, the participants will give the feedback, we'll give them certificates. The certificates will be, of course, the soft copies of the certificates will be mailed to you. There is one question, Professor Bose, beginner in OpenFOAM can join? I think yes, but you can address.
Yes, yes. I mean, I think, as I said, all the technical talks by the experts will give you a perspective overall. And of course, the 5 training session tomorrow will be a very good start for you to use OpenFOAM. Thank you.
So we will take a short break. There can be, I will also want to tell that there can be some delays in between the talks because the experts or the presenters, they are also joining online and there can be issues related, they are joining, etc. So please bear with us. There can be 2-3 minutes delay in each time. So now we'll end up this session, and then in few minutes, in 2-3 minutes, we'll start our technical session. Thank you all.
Yes, sir.
Thank you, everyone. Hello, Professor Kannan. Thanks for joining us. Can you please switch on your video? We can see you. And yes, and can you unmute yourself, please?
Can you hear me now?
Yes, yes.
Okay.
Yes, thank you for joining us. And I really thank you for accepting our invite to actually give us an overall perspective of how we want to promote OpenFOAM in India. So before Professor Kannan starts with his talk, let me take this privilege to introduce him briefly. So hello everyone. So our first keynote talk today is given by Professor Kannan from IIT Bombay. He is a senior professor in the chemical engineering department in IIT Bombay. And apart from that, he has an extensive experience promoting different open source tools in different areas, actually, not only computational fluid dynamics, which is one of this in India. And he is the principal investigator of the project FOSSEE, which is based on free and open source software's education in India. And today we will start this 2-day event with the keynote talk of him, where he will share his overall experience and perspective on how FOSSEE is trying to promote the OpenFOAM tool as a way of promoting computational fluid dynamics education in India. So without further ado, I'll pass over the mic to Professor Kannan. Thank you.
I'm just sharing my screen. Can you see my screen?
Can you please make it full screen?
Yeah, has it come? 1 second.
Yeah.
That is it.
Yes, perfect.
Okay. Thank you, Chandan, for this kind invitation. So the outline of my talk is as follows. In what ways do we promote OpenFOAM? How do we promote? And then some ideas for future work. That is, what are the things we have done here and how do we do this, and ideas for future work. And this is applicable across several other software as well. I'm going to take OpenFOAM as an example here. So the first question to be asked is, should a developing country like India spend money on high tech? This is the question that bothers many people. Fortunately, I have an answer. Here it is. Cyclone Varda, ISRO satellite saved 10,000 lives in Tamil Nadu. This happened 2016. I'm not saying it. This is from a newspaper, Times of India, right? Basically, the ISRO satellite told that cyclone is coming, shift all these people from here to here. Then you cannot estimate its cost, and such a thing should be done for even a developing country is eligible for that, entitled to that rather. So purpose of high tech in India, not just for esoterical reasons, from societal and economical points of view, is extremely useful. Cutting edge as well. You can see that Chandrayaan 1 finds, I can skip this, water on moon. Chandrayaan 2 mission is cheaper than Hollywood film Interstellar. And then Chandrayaan 3 is cheaper than the Bollywood film. Bollywood film is films that come out of Mumbai. Adipurush. The Mangalyaan mission is cheaper than the movie Gravity. In fact, BBC calls it thrilling. Let me click that. Okay. So, which is interesting because, for BBC to say that is something. Now, how do we do this? It is because of the use of technology, simulation. Of course, one can always say that, the costs are lower in India, but then we also have a lot of people. As a result, we do end up putting many more people to do the same task. So they kind of compensate. So this is the Economic Times that explains why ISRO's mission is the Mars mission. Of course, we try to economize as much as possible. Dr. Kalam, Abdul Kalam, who became the President of India, he was working with Agni missile, and he wanted to do wind tunnel testing, and but he couldn't do that. But he found that CFD, computational fluid dynamics, could actually solve the problem, and that required supercomputers, which were also not available to us. One of our colleagues in IISc improved the algorithm to work 10 times faster, so the existing supercomputers were sufficient. And Dr. Kalam became the missile man. Later on, he became the president of the country and so on. OpenFOAM is used extensively by BARC, ISRO, and DRDO labs. By the way, nowadays, you find that you need actually a good deterrent so that people don't attack you. So I conclude by saying that being good in technology is essential for everybody. It is definitely important for a large country like India. Let me briefly mention FOSSEE because this is supposed to be the promotion of OpenFOAM by FOSSEE. FOSSEE stands for Free and Open Source Software for Education. In what ways do we promote OpenFOAM? Large-scale training. We train 100,000 students using spoken tutorials, which I will explain shortly. We conduct many large workshops. So here is a poster that we created. We do something called case studies on OpenFOAM. So we have 150 plus case studies solved by students. These are available here for the entire world. Let me click this. So this is on our FOSSEE website. If you go to fossee.in and look at CFD, you can see that there are 151 case studies. If you click that, any of them, so these are from IIT Bombay, Rourkela, Tribhuvan University, this is in Nepal, this is our neighboring state. So if I click this, you can see that what is the name of this person. We actually recognize this person, where this person is from. These are all extra credits for them, kind of a certificate that they have contributed. One can download the abstract. There it is. So you can see what they have done. Okay. And then one can download the case study and then run it in OpenFOAM. And then I have written a LinkedIn article because if you see there I have classified. I've explained it, but you can see that what are the different models, different problem areas we have worked at, and what are the different institutions that I've worked. Okay, and then statewide split up. Here international, we have only 2 from Nepal. And 25 case studies are in progress. Another thing that we have done is called research migration. You can think of it as a possibly higher level than case study. Take any published solution using proprietary software. Published solution means it has appeared in some conference, journal article, or a book, and so on. Code it in the OpenFOAM. Compare the results and publish. We have 30 plus completed, and it's available here for the entire world. You don't even have to log in. You can just, although there is a login, you can see that I've not logged in. It's still, I'm accessible. It says login because I have not logged in, right? But you can access all of this. So it is the same format. We have up to 33. And these are, once again, here also you see some coming from Tribhuvan University. By the way, these students from Nepal are, they, sometime or other, they work with the FOSSEE project as full-time employees because we are always on the lookout for smart people, good people who know OpenFOAM, for example. Make it slightly bigger so you understand what we are talking about. Okay. So how do we do this? So I have said that we have done lots of these things. Now, how do we do this? Spoken tutorial. This is IT training at a large scale. Large scale means, we have trained about 8 million students in the last 10 years. The main thing is to improve the employment potential at the bottom of the pyramid. For this, we came up with this idea called spoken tutorial. It's a 10-minute long audio video tutorial and to teach open source software. The key thing is these are designed for self-learning. In fact, we kind of guarantee. How do we do this? Through the novice check of the underlying script. This is the thought process. We write a script for every tutorial, which this idea we borrowed from the movie industry. But we don't try to record it immediately. We ask the question, can a beginner understand? Most of the time the answer is no. Then we say, can we improve the script? We send it back. Fortunately, this is not an infinite loop. It comes out. And once it comes out, we record it. We call it spoken tutorial. It is screencast. That means there is a video. My video is not there. My picture, my video doesn't show up. But you can see the video of the screen. And that we do it in English. And we don't make it available in other languages so as to retain employment potential. I'll talk about it shortly.
Welcome to the spoken tutorial on embedding mathematics in XFIG.
Okay, that's a sample spoken tutorial. We dub them into India's 22 official languages.
C++ में constructors और destructors के spoken tutorial में आपका स्वागत है। नमस्कार बंधुगण।
So that is Bengali. I'll go a little faster.
Flow sheeting के அறிமுகம் குறித்த spoken
Tamil.
Java इत्यस्मिन् अङ्कगणितीय प्रक्रियायाः पाठं प्रति स्वागतम्.
Okay. So this helps people who are not fluent in English, whereas the video in English helps retain employment opportunities. It is helpful to people in our neighboring countries because we have common languages. We have some sample dubbing in many international languages also.
Bienvenido al tutorial hablado del
Spoken tutorial در e-card animation با استفاده از
Spoken tutorial về token trong C và C.
Okay. We use simple language. We have more than 1,000 tutorials and we have 10,000 dubbed tutorials into 22 plus languages. Access to internet not required. This is very important because I could conduct workshops for several hundred people in one go. I could even conduct a workshop in Myanmar before the current queue about 4 years ago. Forget about internet, even electricity is a problem there. So everybody uses only laptop and most of the workshop took place in total darkness because they were using the offline version of spoken tutorials. We work only with open source software. We recommend side-by-side learning. Open the video on one side, open the software on the other side, listen to one command at a time and practice. If it works, go to the next command. If not, rewind, listen to it carefully and try again. It will always work because it is created for self-learning. Of course, it is possible only with open source software. We have 8.3 million students trained. We have trained 200,000 teachers. Okay, here are the OpenFOAM spoken tutorials. So you have all of them, once again, accessible without login. I think we are in the process of creating tutorials for the next version of OpenFOAM. And then motivate students we train. Okay, how do we motivate? We give them certificates, give them honorarium. We give them, this is the most important URL of their work, which they can use for jobs, internships, scholarships, etc. And many have benefited. I can give several examples of this, but I have one here. So here is a testimonial given by Sahil from Manipal. So he became a FOSSEE fellow, and then he also got an opportunity to work as a TA in a workshop conducted by FOSSEE. And this OpenFOAM initiative is led by my colleague, co-PI of the FOSSEE project, Professor Janani. And then he went and worked with a multinational called UFI Filters, a multinational company. Okay. Now, I told you about fellowships and internships. We have a large number of students. We have many smart students. But then there could be a mismatch between what their aspirations are and what we want. So what we do is we float typically a screening task because we don't go by the marks that they get in their exams. Sometimes there may not be any match between what they are good at and what we want. So we tell them we are looking for this particular project, somebody, and if you can solve this simple problem in that area, we will take you. We typically take about 100 people, and they work with FOSSEE for 6 to 12 weeks. If it is internship, it is 12, semester-long internship, whole semester. Otherwise, they can do it, shorter period during summer. And this, most of it is done remotely. So in fact, this option is available for experts all over the world. We can actually identify good interns and fellows and offer them to you. Okay, I have come to the third point. What are the things we should be doing, right? I have told you what we have done and how we have done. Now I'll talk about what else we should do. So we could do with lot more international contribution to the collaborative content creation. I'll give an example using DWSIM. This is another software that we promote. Here is another LinkedIn article on that area. Crowdsourced flow sheeting in DWSIM. And why I want, so once again, these are areas. International submissions I wanted to see. So this from Ecuador, there's the DWSIM development team, that means Brazil, students from Brazil, Rio de Janeiro, Brazil, Egypt, Sao Paulo, and so on. So we can do with this kind of contribution for OpenFOAM as well. What else should be done? We can offer FOSSEE fellows and interns to international experts. This is the second one we can offer. By the way, we have already started doing this with our colleague Professor Datta in Turkey. He has taken 2 or 3 of our fellows, summer fellows, if I'm not mistaken. What else should be done? 3, we should do more of lab migration. For example, we have ANSYS Fluent lab based to OpenFOAM are available here. Here it is. There are very few. Shiv Nadar University in India has done one migrated. IIT Bombay has done the remaining things. These are mechanical engineering. These are in chemical engineering. What is a lab migration? What is lab migration? Take an ongoing CFD lab based on commercial software, port all the experiments to OpenFOAM, use them in the curriculum, publish on the FOSSEE website, get an honorarium certificate from FOSSEE. FOSSEE will, of course, organize experts to help if required. What else should be done? Data mining. We have a large amount of collaborative content. Can we mine useful information? I'll explain it with Scilab. Scilab is an amazing alternative to MATLAB. It has excellent computational environment. In fact, French aerospace uses it extensively. In fact, here is, they have launched many of our satellites. Here is the talk by T. Martin of CNES, where he talks about how Scilab is used extensively. They continue to use this. This talk was in 2009, where I was a keynote speaker, but he continues to use it. In fact, he recently asked us for our FOSSEE optimization toolbox, Scilab optimization toolbox, and then we were happy to share that with him. I wanted to talk about Scilab textbook companion because this is also another example. I'm going to talk about this data mining because we have a large collection of useful content created by users, students, researchers, and so on across the world. Can we, make it useful? This is, after all, the AI era. Okay, what is a textbook companion? Basically, students have to give Scilab code for solved examples from standard textbooks. If you do it in Scilab code, then Scilab textbook companion. If you do it in Python, it is Python textbook companion, and so on. Let me explain using Scilab. So basically, it is difficult for students to create documentation, but on the other hand, they are good in writing code. Okay, so if they can do this for, let me just illustrate it. Okay, let me just, it'll be easier because of lack of time. These are all the 633 books for which such Scilab code have been given for solved examples. I'm talking about low-hanging fruit only solved examples. Okay. Let me illustrate it with an example from my area. So let me take electrical engineering. Let me take control systems. Immediately all the books come. Select the book. Here is automatic control systems by BC So let me choose frequency domain analysis. Then I'll select example, let's say body plot. So maybe you can see all this. The moment I select that, this is example 9.15 in chapter 9 of BC in control systems, which come under electrical engineering. So it has come. Now I execute. So I get the body plot. And so notice the shape of this curve. Now I usually give a quiz to all the control people. Supposing I increase the gain, let's say to 5,000, what will happen to the margins? Will they increase or decrease? Well, it turns out that in this particular case, they will decrease. You can run it. So you can see that margins have come down. So previously it was 14 and some 30 odd. Now it has become 8 and 70, which means this is editable. You can actually use it in your classroom, right? So we already have 100,000 examples. I'm doing all this, but something more interesting is we thought, can we give help to faculty members to set problems for assignments, tests, etc. So here is the code search. So where is the code search? You just have to go to, let me just go to FOSSEE.in. In FOSSEE.in, go to Scilab. And there is a search, TBC code search. So supposing I want to do, let's say, partial fraction expansion, okay, in Scilab. So I say Scilab partial fraction analysis. It says the command is PFSS. So I come here, in the 100,000 examples, I search for PFSS. So it has found 140 examples. Okay. And these are all from different books. So I scroll down and go to a book that I'm comfortable with. For example, this book, Kofnor, is a book that I used when I was a student. Then I can download the entire thing, or I can view the code for this example on the cloud. You can see that it has already done. And the PFSS is here. I execute. So I've got the partial fraction. Now S plus 2, S minus 2, and so on. So you can see that it prints only numerator, denominator only. Numerator is not printed because of the semicolon. Let me remove it, run it again. Okay, numerator has come. What I will do is now I can set my own, I just change it from 8 to 7. Okay, I've got that. Now this is a problem that I have set. This is my problem. I can use it anywhere. Okay, which means I have created a platform in which 100,000 examples are there and faculty members across the world can come and use it. Okay, so this is something.
Yes. 5 minutes left in the talk. Thank you.
Yeah, I'm almost done. What else should we do? Competitions. So for example, we did a mapping event. We have a large number of people participating, 10,000 students participated. And then of course, one can also create, coding kind of a thing. Here is a Scilab textbook companion, Scilab Toolbox hackathon that we created. What else should we do? Code development. So I'm not even getting into that collaboratively. These are some of the things that FOSSEE promotes. This is software equivalence. to conclude, open source initiatives are extremely useful for large-scale training. They can also help identify motivated students. In addition to helping students, it can help the trainers as well. It's a way to become a developed country. Join hands with us. FOSSEE project is funded by the National Mission on Education through ICT, Ministry of Education, Government of India. So I'm going to stop here. So if there are questions, I'll be happy to answer. So how do I stop? Stop sharing this. Yeah.
Thank you very much, Professor Kannan. I'll just see the chat if there are any question. Okay, so we have one question from the audience. How much knowledge of OpenFOAM is required for a probable internship with FOSSEE?
Typically, what we do is when we give a sample problem, by the way, the spoken tutorials for self-learning are already available. We might expect the students to learn a little bit. And our people are there to help. The person should be willing to do this work.
Right. Okay, so there is a question on MATLAB and Open Moudgalya. I'm skipping it for the sake of time because this is focused on OpenFOAM. And I would like to thank Professor Kannan again. And I'm happy to share that he has given me the opportunity to become an external advisor of the project. And I'm also supervising some of the FOSSEE fellows and their excellent students. So looking forward to working with you. Thank you. Thank you very much.
And I'm visiting Politecnico Milan. So from where I'm giving this talk. In fact, I'm here to discuss the Open Moudgalya with our experts here. Dr. Francesco Cosella is here, and Dr. Alberto is also here. So we are very happy. I'm thankful to them for making this possible from their labs. Thank you.
Thank you very much.
Yeah.
So I would request Professor Somnath Roy then to add or allow our next speaker if he's there. I see that Professor Håkan Nilsson is present.
Kannan, for your
Yes.
nice lecture and showing us insights on FOSSEE. Thank you very much. So Professor Nilsson is, can you unmute yourself, Professor Nilsson?
Yes, I'm unmuted. Can you hear me?
Yeah, we can hear. Professor Bose, please go ahead.
Okay. Hello, Professor Nilsson. So before he goes with his interesting talk that we are looking forward, let me take this opportunity to introduce him. And it's actually a privilege for me because I sometimes started OpenFOAM at the start of my PhD with some of the content that he created. So it's a real privilege, Professor Nilsson, to and thank you for accepting the invitation to share your knowledge in OpenFOAM here. So Professor Håkan Nilsson, he's a full professor at the Department of Mechanics and Maritime Sciences, Division of Fluid Dynamics at Chalmers University of Technology in Sweden. And he mostly focuses on fluid mechanics, hydrodynamics, and many other things like turbulence. And today he will share his insights on his group's work using OpenFOAM. But I would just like to highlight that he is creator of one of the most valuable earliest repositories of OpenFOAM training. And I'm grateful from all the learners from OpenFOAM to make them available to us. And he is running a course for MS PhD in OpenFOAM for many years now, and which gives people and the students the opportunity to learn OpenFOAM. And thank you for everything. And without further ado, we are eagerly waiting for to listen to your talk and your work on OpenFOAM. Thank you.
Thank you very much. I think you can hear me and see my, let's see, I should also share my presentation somehow here. Oops. So let's see here, share, and this one. So now I think that you can see my presentation. Is that the case?
Yes.
Yeah. Thank you very much for the introduction. Yeah, thank you very much for the introduction. It was a pleasure to listen to the previous speaker, Professor Kannan, who I really enjoyed this effort to try to spread knowledge in OpenFOAM and other softwares as well. And as you heard, I have been trying to do that many years as well myself. So I'm happy that people are using that material. So yeah, today I will talk about some research that we're doing in my group. Our main field of research is within hydropower. So what I will discuss today is studies of transient operation of hydraulic machines using OpenFOAM. So first some short background on the objectives of this talk then. Water turbines are more and more used to stabilize the electric grid, both in terms of power availability and frequency. And that is because there's coming more and more renewable energy sources like wind power and solar power into the grid system. And those are intermittent, and therefore something else has to make sure that we always have the power that we need and the correct frequency in the grid. And there hydropower comes into play. The problem with that is that then we will have new operating conditions for hydropower and new problems in hydropower. Also, we need to store energy from when we have an excess of electricity until we don't have enough electricity. So pump turbines is also something that is increasing now more and more. Pump turbines can vary the conditions and even revert the operations from pump mode to turbine mode. So you pump when you have excess electricity and you run in turbine mode when you need to generate electricity. So the problem now with these new conditions is that we will be running much more at off-design operation conditions. We will start and stop the machines frequently, vary conditions, and running at something called speed no load. That is when the machine is running at full speed, but there is no load on the generator. That creates hazardous flow-induced instabilities, and we also need to determine optimal operating conditions and operating sequences. From a CFD point of view, the requirements are then to have partly rotating mesh and sliding interfaces. We have changes in blade angles, mesh morphing, and we also need to do solution mapping between different meshes during the simulation. In Kaplan turbines in particular, we also have changing of blade angles inside the rotating domain of the simulation. So this mesh morphing that we have to use then for those blade angle changes happens all over the domain, but in particular you have also some tiny clearances which are quite problematic. And we also need some special boundary conditions for system dynamics. So let's move on to an example then of a water turbine, which is called the Francis 99 water turbine from NTNU in Norway. So to the left we see a top view, and to the right we see a view from the side cut through the domain. So the water is coming in through this pipe here, going to stay vanes and to the guide vanes and into the runner. And the guide vanes can change their angle, but the stay vanes and the runner blades have fixed blades in the Francis turbine. If we look at the side view here, we can see that this spiral casing here, same as the outer part of this picture here. Then we have the stay vanes, the guide vanes, and the runner. And then the flow goes into an expansion here, into a draft tube going to the lower reservoir. So what they have measured in Norway is in particular then a PIV plane here. If we have a sketch of the runner blades here and the initial part of the draft tube, there's a PIV plane here where they have extracted velocity data across at those three lines here that we have a look at now. Just to start by validating, of course, with the best efficiency point conditions. So we have the three columns here for line 1, line 2, and line 3. Those marked with different colors, and we have the horizontal and axial velocity component. The experimental data is with markers, and the OpenFOAM results is with the line. And as you can see, we're fairly close to the experimental data, and there's a slight shift in particular in the horizontal velocity, but that we believe is a shift in the experiment, which is not really expected. So at least we are very close to the experimental data. But that was at best efficiency point with a steady operating condition. We want to do transients, and in order to do transients, we need to change the guide vane angle while the runner is rotating. So we have here a mesh of the computational domain with the runner at the bottom here, and we have the guide vanes at the top. And between the runner and the guide vanes, we have an interface here, which is a sliding interface where you use an AMI interface, arbitrary mesh interface. And the guide vanes are, while the runner is rotating, we can see that the guide vanes are changing the angle. I will put the laser pointer here so you can see that the guide vanes are changing their angle. And we're squeezing the mesh, and eventually we also need to exchange the mesh and do mesh more to map the solution to a new mesh. So when we do this, we can of course study the flow inside the turbine. Here's an example of startup to best efficiency point. So we start from almost closed guide vane angle, as we can see in this graph here. This is the guide vane opening angle starting from 0.8 degrees. They are closed here, as you can see in this mesh image. And then the guide vane will open up to the best efficiency point condition. So you will see the guide vanes opening here. You will see the flow developing in the draft tube here using the lambda2 isosurfaces. And yeah, I'll just start this animation here. So you can see then that the guide vanes are at a particular closed angle here, and after some time they will start to open. We see the vortices in the flow by the lambda2 method. And the guide vanes start opening here, and you see the flow developing here. And to the right, you can see then the pressure in the draft tube and the horizontal force on the runner while this is happening here. So as you can see, after some time, when we reach the best efficiency condition, we focus the vortex in the draft tube to the very center, and there's almost no swirl in the draft tube at the best efficiency condition. So let's move on to the load reduction case then, which is another animation where we start from an open guide vane here, and then we close the guide vane slightly. So we start at the best efficiency condition here, and then we go down to some lower value, not closed, but a lower value. Again, we have the lambda2 isosurface to visualize vortices. We have a vortex in the center at best efficiency condition. Now soon we start to close the guide vanes. As you can see here, they start closing, the runner is rotating, we start forming a vortex in the center, and we get the force on the runner and the pressure in the draft tube here in two different graphs. We have the rotor-stator interaction in the graph, the fastest frequency, and we have some slower frequencies developing. And in particular, as you can see in the isosurface here, that we get a vortex that is oscillating in the center, a helical structure called the vortex rope. And you can see that gives pulsations on the force on the runner, and also pulsations in the pressure in the draft tube. And that can cause problems with the machine, deteriorate the machine, and so it might even break, and there may be accidents. So we have done this also for shutdown and startup sequences then, so we can go from the best efficiency point down to some completely closed, almost closed here. We cannot close it down to 0 degrees. We have to keep some cell between the guide vanes. And we get some kind of pressure pulsations here in the vaneless space between the runner blades and the guide vanes, as you can see here. So we have mostly rotor-stator interaction, but we also get pulsations here due to the vortex rope during some part of this transient. Similar for startup, we go from a small angle and go up to a larger angle for the guide vanes, and we get some signal here. And as you can see, we have both the numerical and experimental results on top of each other here, and they are quite similar. We can also look at the line 2 here in the experiment from the PIV measurements, and look at during the shutdown sequence, the left part here, and the startup sequence, the right part. We look at the axial velocity along the line here from left to right is from 0 to 1 here, and on the y-axis we have time. So and on the top we have the present study numerical, and on the bottom we have the experiment. So without going into details, you can see that the numerical results at the top and the experimental results at the bottom here during the shutdown sequence, as we go from bottom to top here, they look very, very similar. And also for the startup, we go from bottom to top here. Also here, the experimental and numerical results are very similar. Similar for load rejection, so I'm not going into the details of this graph, but they are in principle, you can interpret them themselves the same. You can see here some development of this vortex rope, both in experiments and simulations. So that was Francis turbines, and we had only guide vanes that change their angles in Francis turbines, but in Kaplan turbines we have both guide vanes changing angles and also runner blades changing angles at the same time as the runner is rotating. So here we see that we can actually change the angles of guide vanes and runner blades at the same time. So the guide vanes are moving and the runner blades are moving. In this animation, you don't see that the runner is rotating, because then you would not be able to see that the runner blades are actually also changing their angle. In fact, the runner is rotating here. We only visualize when they are in a particular position. So we have used, and also we have developed this to make sure that we don't destroy the mesh. So here we see some different views of the guide vanes, and in particular some top view here. You can see that the bottom surface below the guide vanes will turn and go axially downwards into the turbine. And that means that the guide vanes are going over a curved surface here. And we need to then change the guide vane angles, as you can see here. And the mesh points on the lower surface must slip on this curved surface. In the upper right, you see a zoom in of the lower part of a guide vane where there's a clearance. And if I animate this, you can see that the points are slipping on the lower surface here. And it's very difficult to make this work without destroying the mesh. In the lower right, you can see a zoom in another view of the same thing here. So this is something that we developed. It's not actually part of OpenFOAM. This slipping algorithm, you can find it in a paper, Computer Physics Communications, where you have also test cases and things that you can take them and develop them for your own sake. So we have then compared OpenFOAM, the standard version, the standard slipping algorithms in OpenFOAM, and also our new developed method for slipping on the lower surface, and also ANSYS Fluent and ANSYS CFX. So what we see in the right here is the number of severely non-orthogonal cells larger than 70 degrees here. In the standard version of OpenFOAM, we see that this red curve goes up rather fast. If we look at ANSYS CFX, the green curve they maintain a good mesh quite a bit longer, and ANSYS Fluent, actually the black curve, it stays at quite low values. But the problem is that those dotted lines here are when we have the first negative volume cell, which happens for ANSYS Fluent at this point at 6 degrees approximately. For the original OpenFOAM, it happened very quickly. For CFX, it happens here, and for our developed method, it happens over here. So we have a huge improvement in the mesh morphing and slipping on curved surfaces with this development. So we use this to study then the transients in Kaplan turbines as well. As you can see, the vortices at best efficiency point and part load. And of course, we analyze the flow in many other ways as well. Here's an example of a spectrogram, short time Fourier transfer. It's a pressure signal in a point in a draft tube during a load rejection. And we can see over time here the frequencies. And in particular, we have the runner blade passing frequencies and its harmonics. And we have the guide vane passing frequency and also the frequency of this rotating vortex rope. And also it will break down at some point here. So we see a large spread in the frequencies. So coming into pump turbines, I would like to mention a project that is an EU project that is about to finish right now with several universities and one company called Advanced Design Technology in London, who have collaborated to design a new kind of pump turbine, which is economically viable low head to ultra low head pumped hydro storage. And the heads should be 2 to 20 meters and the power 10 megawatt per unit. We need to have a round trip efficiency of 70 to 80%. So that you get back approximately 70 to 80% of the electricity that you put into pumping, you get it back by running in turbine mode. So we want to use this to increase the grid stability and enable pumped hydro storage to unexploited sites. And also in the project we assess environmental and ecological effects. We have people working in different areas: fluid dynamics, electrical, civil engineering, biology. So we have been working, of course, with the turbine itself, the flow in the turbine using OpenFOAM, but we have collaborated with this company, Advanced Design Technology, ADT. They were responsible for the actual design of the turbine. We have been responsible for the simulations and studies of transient operation of the pump turbine. But we also compared OpenFOAM with CFX, as we can see in this slide here, where we have done similar simulations as they have used with CFX in the design, which is a single blade passage simulation using mixing plane and cyclic conditions on the sides. We can use cyclic GGI, general grid interface, which comes from the FOAM Extend, or AMI, which is from the regular OpenFOAM version. And this mixing plane has originally been implemented in FOAM Extend, but now it has actually been also merged to an external library for OpenFOAM, the ESI version, so it is available to download from the Turbo Machinery special interest group, where you can find that code to download. So to the right, we can see that we have quite good comparisons in pump mode and turbine mode for head efficiency and power, comparing CFX results from Extend and OpenFOAM version 2306 with GGI and AMI. So actually also the GGI interface has been ported to the ESI version, as well as the mixing plane. And the mixing plane can be used both with AMI and GGI. Those GGI and AMI together with mixing plane actually gives exactly the same results as we can see in the plots here, and we get fairly similar results between all those versions of codes. Okay, so let's have a look at some examples here. Experimental facility for an optimized model scale of this turbine that we have developed, which is a contra-rotating device. I didn't mention that before. It is actually, instead of having guide vanes and runner blades, we have two runners which are rotating in opposite directions. So this device here is put in an experimental facility, as we can see down here. The numerical domain is this marked region here, and the machine is in this region. And then we have an elevated tank with an elevated water surface and a lower tank here. And of course, in turbine mode, the water will go from upstream, from the elevated tank to the lower tank, and in pump mode, it will go the other way. In this system, we have different losses. We have losses in pipes, valves, bends. We have some instruments that also have losses. We have inlet-outlet losses in the tanks as well, and that we need to model. But those are not part of the computational domain, so we need to put them on the boundaries of our CFD domain. So we have developed a boundary condition called head loss pressure, which is published in the OpenFOAM journal. We encourage everyone, of course, to publish in the OpenFOAM journal. It is it's free to publish. No, it doesn't cost anything to publish. It doesn't cost anything to read, and everything that is published there is reproducible as well. You can just download everything that you want to get. It's a double-blind review process. It's a proper review process, so you can really you should publish good papers in that journal. So we apply Bernoulli's equation on the patches of our domain here, and so basically it is the Bernoulli equation, as we can see here on the patch, setting the pressure. We also have local and friction losses in the part of the domain that is outside the CFD domain. So in this case, of course, we assume that the velocity at the reservoir surface is equal to 0. So we can have, in this boundary condition, we can have any number of local and friction losses that happen outside the CFD domain. We have time varying possibilities for the head and also one minor loss, for instance, a valve. For inflow and outflow, we have to subtract or add the losses because of the direction of the flow. This is developed for incompressible flow, and one output of the simulation will be the flow rate. We don't set the flow rate, we set the head difference, and then the flow rate will be given in both directions. And this is important for pump turbine simulation. So some example here, and just numerical properties. We use, in this case, version 2012, the ESI version, use head loss pressure at both ends for pressure with some gross head here. Pressure inlet outlet velocity at both ends. Turbulence model is Keomegesis TSAS and 12 million cells. We have different regions here. We have low pressure zone, runner 1, runner 2, and a high pressure zone. An AMI interface to transfer the fluxes between the rotating and non-rotating parts, and individual runner regions then that are rotating. So here we see some results then. So the computed flow rate is 285 liters per second at 90% efficiency, and we see the velocity magnitude on a cut plane through the machine. The flow is from right to left here in turbine mode, so you can see the flow features. And we see flow structures with the lambda 2 methods here, for instance, the horseshoe vortex, some vortex shedding after the struts, and we see blade tip vortex. And same for pump mode, we get 267 liters per second at 87% efficiency, and we see the velocity magnitude here again. From now the flow is from left to right, and again flow structures with lambda 2 method. We see horseshoe vortices, vortex shedding, and blade tip vortex. And we can just have a quick look at what it looks like when the machine is operating here. When we start from a condition where there is 0 flow, when we put the valve at the boundary condition here to stop the flow, and then we open the valve after some time, so we allow the flow to go from left to right in this case. Of course, we can extract the forces on the runners happening here. To the left, you can see the valve that is modeled using a loss coefficient. Finally, we have done optimization of the pump mode startup sequence. In particular, it's difficult to determine how to operate the machine in pump mode. So what we want to do here is to minimize the objective function to prevent severe load fluctuations. So the objective function is to minimize the gradients of the time gradients of the forces on the runners here, as we can see. And we have a design space here where we allow the valve to operate in this gray area over time. And we have the runner rotational speed should start from a particular value 0.6 here, which corresponds to a value where they counteract the gross head. So when the valve opens, there will be 0 flow. And then the operation of the runner rotational speeds can then vary inside this red region. So we have done 250 simulations of full transient sequences, and those transient sequences are like 10 seconds or something like that, and you can imagine that it takes a lot of time to do all these simulations. So we ended up starting with the curves that have boxes on them here, which is the baseline case. We ended up with some other suggested way to run the machine here to open the valve to change the runner rotational speeds individually. And with that, we were able to reduce the maximum force on the runner. So this curve here is the baseline case force on runner 2, which has a peak here, and we were able to reduce that peak, so it is much smoother. Same for the torque. So yeah, I need to finish, so I thank you for your attention, and also I thank this Alpheus project, the EU project, and the Swedish Center for Sustainable Hydropower. NICE is providing the computational resources together with C3SC. Also thanks to OpenFOAM developers and community, because we are working together, we are using what others are using, we are contributing to other people as well. In particular, I want to mention my colleagues here, Dr. Said Salehi here, and soon to be Dr. Jonathan Fahlbeck here as well. He's defending his PhD in fall. Thank you very much.
Thank you, Professor Nilsson, for your very insightful talk. I think we have got many questions here, but for the sake of time, I will be only taking a few, and we can discuss the rest later. So basically, one major question people have asked that the attractive animations that you have showed, what is the tool that you have taken to prepare the maze for those problems?
So we are unfortunately not using open source software for meshing. We use various ways of meshing. Our main tool is use ANSYS ISM CFD for the meshing, but we use others as well. Yeah, it can be.
Right.
It can be. Yeah.
And another, I think, relevant question is that someone has asked, have you done the whole simulation in 3 dimensions, or did you use some symmetry surfaces, and which solvers did you use in OpenFOAM?
This is done with the PimpleFOAM, the unsteady simulations, and it is full 3D simulations in all cases except for when we do the comparison with the design simulations, as I showed before. So this is just it's still 3D, but just single blade passage. But in all the other simulations, all the animations, we use the entire geometry 360 degrees.
All right. Okay. I think I can take one last question. Someone has asked if you can comment on the computing time for these 3D simulations.
Yeah, so typically one of the animations here, like this one, takes, this is 12 seconds, starting from 0 to 12 seconds, and we use approximately 300 cores, and it takes about 1.5 months. So it is quite heavy simulation. If you recalculate that to single core, it would take 40 years to do the simulation. So we're glad that there are parallel simulations.
That's impressive. That's a very impactful statement you've made, I have to say.
So still, this is with this is with K-Omega SST SAS, so it's not fully resolved. Unfortunately, we cannot do LES simulations of this. That would take much too long time. But right. We do LES simulations in other cases, of course. And in particular, the Timisoara swirl generator, we have done more resolved simulations. So, of course, there are many more things that I could talk about, but I had to fit this into this time.
Sure. So let's thank the speaker again, everybody, virtually. And thank you again for sharing your insights. Before you leave, I just want you to briefly comment about the Turbomachinery Special Interest Group, just for the other people to know about it. That will be good.
Yes, so we have a Turbomachinery Special Interest Group that is part of the OpenFOAM governance, and where we try to identify which developments are needed for turbomachinery in particular then. So I'm working mostly with incompressible flow, but there are some people who work with compressible flow as well. So we identify what is needed to be developed. We develop tutorials as well, and test cases for turbomachinery. I'm just right now working on changing some tutorials from Extend to the ESI version, because we are now merging everything into the ESI version. So you can find it on the openfoam.com. They have a page, a wiki for those this OpenFOAM governance, and there you can find different special interest groups and working groups for different areas, and among one of them is the turbomachinery group. And actually, we started already in 2007 the first time, I think. But then we worked many years to develop the GDI interface so that we could do these kinds of simulations. And now we have again a group more focused on the ESI version rather than we used the FOAM Extend version before. Please get in touch with me if you want to know more about something I talked about. You have my email address here, hakan.nilsson@chalmers.se. So I'm here for you.
Yes, thank you very much. So we have our next speaker already with us. Thanks, Hakan, again for sharing your knowledge. So let me now take the opportunity to introduce Professor Gavin Tabor from University of Exeter before he shares his work on OpenFOAM with us. Again, thank you, Gavin, for joining us and accepting our invite to share your knowledge with the audience, the broad audience, mostly students and scholars. So let me briefly introduce Professor Gavin Tabor. So he's a member of Center of Water System and Computational Engineering Group in the University of Exeter. And he's also chairing the OpenFOAM technical committees, and he is an extensive contributor to the body of knowledge in OpenFOAM that has been gathered over years. So we are, again, we are very much glad to have him within us. And today he will be actually talking about his research on combining Bayesian optimizations with OpenFOAM for industrial multiphysics problems. So without further delay, I would hand over the mic to Gavin.
Thank you very much, Chandan. It's a real pleasure and honour to be able to speak to you today. And this is the first UK-India or India-UK symposium, and I'm sure it won't be the last. I have a very wide range of research interests. I always have difficulty deciding on something to talk about. But today I've decided to talk about something I've been involved with for a number of years now, which is using automated techniques for optimization and linking them up to CFD. The title here, and a bit of explanation, Bayesian optimization is a methodology which has come from machine learning. I'm sure I don't need to say how much of a hot topic machine learning is these days. It really is revolutionizing CFD and giving us a whole range of new techniques. I think a lot of people possibly think of machine learning as being a synonym for big data, data science, but in reality, machine learning is any algorithm which is not programmed directly, but learns from its input data. And Bayesian methods are tuned for learning from small amounts of data and extracting the maximum amount of information from a limited data set, which, as we will see, is quite important if the data set is coming from expensive CFD simulations. That being so, I'll start off by just doing a quick signposting to the talk. I'm going to start by introducing optimization methods, and in particular talk a little bit about this Bayesian process, which you may not have come across before. And then I'm hanging the talk on industrial applications for this. And so I've picked 3 cases we worked on over the last few years, which are increasingly sophisticated and more real world as we work our way through. I often like to say that CFD is driven by Moore's law. Each year, computers get faster and better, more parallelization. Thank you, Håkan there. And the question in CFD is, what can we do with that increasing computational power? And obviously, we can use it to generate more faithful models, higher fidelity, larger meshes, more complicated physical modeling. We can also just run more simulations, and we can use it as a design tool, which of course we've been doing for years and years. in all industries, people run CFD models and then fiddle with the geometry or the inputs and so forth, and use it as part of the human-inspired design process. But there are a lot of reasons why we might want to automate that process. It takes the human out of a loop and go off and do something more valuable while the thing's running, but also removes any possible human bias about what might be the correct solution here. Of course, we might also want to mine the human knowledge of the process, but automating it has a lot of benefits. Now, obviously, in optimization terms, there are many different ways of doing this, and some are gradient-based approaches. And in CFD, this is things like adjoint optimization, which has been extensively used in the automotive industry. But evolutionary approaches, genetic algorithms, are also available, and they have a lot of strengths. Now, I'm sure we're all aware of how GA works. You create a computational representation of your parameter space as a genome. You create a population with different genomes. You assess the fitness of each element there, kill off the worst performing ones, and create a new generation through swapping and mutation and so forth. And GAs are well known to be very effective with large but not necessarily huge dimensional parameter spaces. They only need you to evaluate the actual fitness itself, and they're very good at identifying global optimal solutions and don't get stuck into a local maximum or minimum, basically. But you do need to evaluate the fitness function, and you need to do this repeatedly, thousands or maybe even tens of thousands of times. And if that's running an expensive CFD model, that may not be feasible. Of course, we can get around this if we introduce a surrogate model here. So a surrogate model is a cheap computational and mathematical model which can be fit to a limited amount of data. So we can run our CFD model tens or maybe 100 times to explore the parameter space, and then use the surrogate model to interpolate on the results. And then, having built the surrogate model, we can then do the evolutionary optimization using that to determine the fitness. And this can be very valuable, and I've added a few colorful diagrams here for some work I've done with a air conditioning fan manufacturer doing exactly this. But it's not completely perfect. And in particular, since we are building the model, then using it to optimize, we are constructing our surrogate before we know which areas of parameter space we might be interested in. And these may not be the areas which we have adequately explored in our surrogate model. So this brings us on to actually Bayesian optimization, because it suggests that the way forwards is to focus on the surrogate, and we can build an algorithm which iteratively updates this surrogate as part of the optimization process. Now, I've included a diagram which I unashamedly stole from the internet here, which illustrates the process in one dimension here. So our Bayesian process actually has two functions. What we're trying to do is to optimize the solution, which is this cost function, this solid line, which we don't know. So we have an approximation, the objective function, which will be a Gaussian process, and that's an approximation to this which agrees at our observations, but away from there gives us an estimate. And since it's a Gaussian process, it also gives us an uncertainty range represented by this blue section here. Also, we have an acquisition function, which is this green thing here, and this is used to identify the best location to do one further evaluation of our model, in our case, this expensive CFD model. So you can see here that the optimum solution seems to be around this point here, but the uncertainty in the, I hope you can see my cursor, I'm gesticulating with it, the uncertainty in the Gaussian process suggests there's an outside chance that the optimum might be to the left of where we actually think it is at the moment. And our acquisition function correctly identifies that and suggests, right, we need to run the model here in order to check that the optimum is actually this black spot here, not the red spot here, and so forth. So overall, we're going to start with a coarse-grained surrogate for the system, sample the points in the parameter space with something like a Latin hypercube, and then entering the optimization process. Each iteration, we do another evaluation to improve our knowledge of the objective function. And this is why it's Bayesian, because you are deciding where the best place to go given the information you already have, and it's a machine learning algorithm because it's learning from its input data. It also, as we'll see, massively reduces the required number of function evaluations, which is really important given the expense of the CFD. Now, quick bit of background. Some years ago now, some colleagues in computer science invited me to join them on an EPSRC project to look at this. I have unashamedly benefited from Richard Devison and Jonathan Fieldson's knowledge of the methodology here, and we've done a lot of work. My first two examples were things which we did with this particular project, and then after that, when my industrial contact, Hydro International, decided they wanted to take this further, and the third example will be something which they brought to the table to work on. So my first industrial problem, we made it massively simple to explore the technique. It's a simple cross-flow heat exchanger. We've simplified it enormously, so it's a two-dimensional case, so it'll be quick to run. We're heating up a fluid coming in blue, going out red as it goes left to right, and the individual pipes are constant temperature surfaces. Low Reynolds number, so we can run steady state and no turbulence model. And what we're trying to do is to optimize the system in terms of the placement of these cylinders and their size. Now, of course, there are two. It's a multi-objective optimization. We want to maximize the heat transfer, but at the same time minimize the pressure, the frictional losses, i.e. the pressure drop. And these two are antagonistic because we can increase the heat exchange by increasing the area, but also increases the drag. So running our Bayesian process, we get a number of samples here, 270 altogether as part of the overall process, and plotting them in terms of the outputs, the pressure difference and the temperature difference, we end up with a Pareto front, a set of points here representing the trade-off between maximizing the temperature difference and minimizing the pressure difference. So these are design choices. And over here, one of those design choices has been illustrated. Very odd solution, but that is an optimal solution for this particular problem. There's always an element of stochasticity in the method here. So the team fiddled with the inputs and ran some other ones. So here again is another evaluation run, another optimization run, 400 evaluations, but again, a Pareto front giving the balance between friction and heat transfer. Moving on, my second example is one which Håkan will recognize. He's already mentioned draft tubes in his presentation. It's a very interesting problem to try and optimize. losses. So the draft tube takes the water out of the hydroelectric turbine here and returns it to the natural environment, a river, a lake, or something like that. And he undoubtedly would have understood this immediately. I didn't. I had to learn that the design of this draft tube is quite sensitive and quite important. And again, there are two parameters here. We want to optimize the pressure behind the turbine, but at the same time, we want to minimize the frictional losses on the draft tube surface. Now, a lot of research has been done in this area, and in particular there's been a series of Erkhoff-Tak workshops investigating this Hollerforce and Kaplan design. And so this gave us a baseline case to try and optimize, and a great deal of background knowledge, of background wisdom from people like Håkan on what to do, particularly in terms of the CFD. So we were able to use best practice for doing the simulation, and also do some quite extensive mesh refinement and validation study to demonstrate our results were coming out correct. Multi-objectives, so we're optimizing for the pressure recovery factor. We want higher is better, but also skin friction, smaller, lower frictional losses. Both can be evaluated here. And now we've got a more complicated geometry. It's three-dimensional. The team broke it up into several different sections with different parameterized CAD models to get the geometric variation, and different meshing techniques to create the meshes. We're able to do the calculation. Here, this star here is the baseline case from the Erkhoff-Tak series, but with 200 evaluations of our CFD model, we were able to again generate a Pareto front, giving the trade-off of friction factor and pressure drop, and some of the Pareto front designs are shown in this particular thing. Now, 200 is still quite a large number of evaluations. Luckily, we have access to a supercomputer called Isambard, and we made extensive use of it. It's a reasonable number that we could run several times and explore the possible variability of this Pareto front. Now, a couple of weeks ago, I got a very interesting paper on in my scientific feed. It's by two researchers in the Czech Republic, and they've done a similar optimization process, but using a genetic algorithm directly driving a CFD code, actually Fluent. And it's an excellent piece of work. I'm not disrespecting what they've done, but I pulled out, they took 4,000 evaluations in order to do their GA directly, as against our methodology taking 200 evaluations. As I say, it's a good piece of work, but this does illustrate an order of magnitude improvement in the number of evaluations necessary. Right, I now want to move on to my final example, and it's from a company called Hydro International, who I work with quite extensively, and they were very interested in this technique. They are in what's called sustainable urban drainage, so they design and manufacture devices for controlling stormwater surges, purifying water, and so wastewater and so forth. One of their products is this head cell separator, and it's basically used to remove particles from wastewater by forcing the water to circulate around these conical plates. The interaction of the boundary layer encourages the particles to drop out and down into the base here, so it clarifies the water. It's basically a Dyson vacuum cleaner for water. They wanted to improve it to optimize the design, so this made really quite a good case to look at. It's a multi-physics problem, so we are dealing with both a fluid flow problem, so we used simple foam to do a steady state simulation, and then tracking the particles through, and this is an animation of the process working like that. It's a much more complicated problem against a real industrial problem. So we're going to use a Bayesian optimization process. We have a parameterized CAD model, but our parameterization, there are regions of the space which are either unmanufacturable or inappropriate for the constraints here. So we have to focus down in a particular area. We build multiple surrogate models for the different aspects of the problem here and run the calculation, run the optimization until we run out of computer time and the guys on Isambard tell us to stop, basically. Now, there are a couple of significant aspects of the process which we explored with this very realistic case. One is meshing. We all know how difficult meshing is, and that's doing it as a human being interactively where you can recover from problems. Automating the process, we need it to be robust to failures in the mesh. So we explored building a further surrogate model which could learn aspects of the meshing in order to improve or avoid errors there. The other thing is parallelization. My computer science colleagues wanted to run the algorithm sequentially, but we have a large number of nodes available on Isambard, and we need to parallelize this aspect. Obviously, the CFD were running in parallel. We also wanted to parallelize the search as well. So we investigated various different ways of doing that. And the result, again, was a very nice optimization. Here's the end result, but I've got an animation to show you, and each of this is animating the evaluations of the different cases. Each of these new points represents nearly a day on one node of Isambard, and you can see our initial sample over here had 1 point down in the exploration region down here, and the algorithm quickly identified this was the region to explore and created our optimal Pareto front down there. Significant improvements, and the new design is something which Hydro has now put in a patent application to protect. I am personally on a crusade to stop people treating machine learning as a black box process. So having found an optimal solution, the other thing to do is to check it and to identify the physics as to what's going on here. But that is something which we took over. So to conclude, we can do automated optimization, and things like Bayesian optimization can be very valuable. There's still a number of important challenges, mesh generation being one very significant one, but also how to parameterize the problem, how to run it in parallelization and so forth. But one big aspect of Bayesian optimization, though, is that it only requires function evaluation, which opens a route to our multiphysics, to, in this case, particle tracking, but also FSI, error acoustics, and so forth. Final slide to acknowledge my wonderful research group, my colleagues in Exeter and elsewhere, and also in various companies that I've worked with, and some papers where we've published or hopefully are going to publish the results of our work. So thank you very much for your attention. I will try and answer any questions in the remaining, 5 minutes or so.
Thank you, Professor Tabor. I'll try to pick up a few relevant questions from the chat box for you. So I see that Harish has asked, can you recommend some surrogate modeling techniques for CFD simulations?
We've been using what are called Gaussian process emulators, and they're quite valuable for this. A Gaussian process emulator basically is an ensemble of interpolations between the points, and that gives us not just the most likely interpolation between the points, but it also gives us the distribution of uncertainty as a Gaussian probability distribution, basically. But that's important here because it's part of the process, but it's valuable in a number of other examples because it gives you that uncertainty estimation.
All right, thank you. Sivam has asked, does MACE needs to be same for all the training cases for the code, or it can be different MACEs?
Well, that's a really good question. It's something I'm hoping we're going to explore eventually. There are various ways in which we could make this a bit. At the moment, we're doing what we usually do in CFD, which is to validate on a mesh construction methodology, not a specific mesh, but y plus value of this, growth of boundary layer, size of domain, things like that, and then saying, right, when we move to a slightly different case, if we construct the mesh the same way, we have our certainty that we're still getting the right answer. So in that sense, we are building a CFD workflow here which generates similar meshes for each case. But of course, you could imagine a case whereby a really detailed mesh might be something you could avoid. So if the algorithm is exploring a new solution, maybe it could do a cheap, low fidelity run on a coarse mesh and determine from that whether or not it wants to do a more detailed run. If we do a low resolution mesh and find the solution is completely and utterly wrong, then maybe we can just throw that away. So we are going to be exploring multi-fidelity as an aspect of the solution process, of the optimization process here.
All right. For the interest of time, I'll just take the last question. The last question, someone has asked, what's the learning pathway to become a CFD machine learning engineer?
Yes, I wish I knew. I've been doing my best myself. I'm lucky. I have various colleagues in computer science and elsewhere who have been in this area for a long time. I'm sure everybody in the audience has great skills in CFD, and we know how challenging CFD is. Machine learning is a whole new book. Lots of new techniques there, but obviously a lot of study needed, and it's so novel. The set of information we need to understand is constantly advancing. Luckily, as with OpenFOAM, in machine learning, there are a whole slew of resources online. I learned a lot from a course on Coursera, the online platform, given by a Professor Nug, NG. I have no idea how that's pronounced, but he is a very significant person in machine learning. It was a great experience there. There's also one or two people on YouTube. I was about to say somebody's name. I'll put it in the chat, but there are one or two people posting on YouTube videos on machine learning in CFD and in fluid dynamics. Andrew Nug, yes, well, thank you very much.
Thank you, Professor Tabor. Can I request you to say a few words on the OpenFOAM technical committees and their activities?
Absolutely, very happy to, yes. A few years ago, Fred Mendonça, who I'm sure many of you know, he's the managing director of OpenCFD, established this governance process. So the idea was to bring in important members of the OpenFOAM community, so academics, companies who use it a lot, to help OpenCFD identify where to take their branch of the code and the code overall. There's, I'll just hang around. There is online quite a lot of information. So if you look up OpenFOAM governance, there's some information here on their website, the steering committee, who's on it, and you can see you've got Volkswagen, General Motors and so forth, but also the technical committees, which as last speaker commented, we have technical committees covering a number of different aspects. Josef Naj, for example, documentation and so forth. Turbo Machinery is Håkan and so forth. The individual committees are in touch with their communities. They try and identify both challenges to work on, but also solutions which are coming out of their communities, and try and feed them into the governance process. And I am chair of these technical committees, so it's my job to try and liaise, to try and identify from what they bring to me what are worth investigating and take it forwards with the governance process.
Thank you, Professor Tabor. It was really insightful presentation, and on behalf of all the audience, I really thanks a lot. I convey our thanks to you for joining us and sharing your work with us.
Pushkar has identified the name I was searching for. It's Stephen Brunton. He has published several review articles in things like annual reviews of fluid mechanics, but has also got a lot of videos on YouTube on machine learning.
Yes.
Thank you,
He's very
Pushkar.
popular.
Yes.
Yeah. All right. Okay. So our next session of this conference actually comprises of a panel discussion. So I would request Professor Tabor to be with us because he's one of the panelists, and we have our two other panelists already added as participants. So can I request Professor Atul Sharma from IIT Bombay to unmute himself and switch on the camera? And I will request Professor Somnath Roy, who is the co-chair of this symposium, to unmute himself. And I will take the privilege to moderate this session. And so let us actually thank the three panelists to be with us and discuss this issue with us in the context of both UK and India and where we stand. And I have actually got a few questions from different audiences, and we'll try to discuss that. But I will also take questions from the audience. So please feel free to ask in the chat box if you want to actually discuss something with us in this 1 hour session. So before we start, I think I would like to introduce Professor Atul Sharma and also thank him to join us in this panel discussion. Professor Atul Sharma is actually now, if I'm right, he's the head of the Department of Mechanical Engineering, IIT Bombay now, and he is a pioneering contributor to the computational fluid dynamics in India through developing his own codes in research group. And I'll also tell that we have actually looked forward to his work when we were students as PhD students. He has written a few books on the computational fluid dynamics, which is actually very much useful for the student. So Professor Atul Sharma, could you please tell a few words about your research and work in IIT Bombay?
Yeah, thanks Chandan for the kind introduction and kind words. The way I had been trained in Indian Institute of Science Bangalore and in IIT Kanpur, that is around 25-30 years ago, where in India, especially in academia, there were as well as in worldwide, there were a lot of in-house code development. So I got the training on single phase in-house code development, mainly by Professor Ishwaran from IIT Kanpur, which greatly helped me to take that forward And in fact, Professor Ishwaran has developed in-house, I would say, open source code for Bhabha Atomic Research Center. BRC has taken a big project on that. And after joining IIT Bombay, I started developing codes for, in our research group, we started developing code on level set method based method for multi-phase flow simulation. So there were a couple of PhD students who worked on code development through level set method. And then in the level set method, we started with a diffused interface method. Then we moved on to sharp interface level set method. And after multiphase flow, we switched to fluid structure interactions because especially after I'd written a book on CFD, where I gave a new perspective, more of physics, less of math, especially to make CFD easy enough to be taught at early undergraduate curriculum. So I want to extend this idea for solid mechanics also. So from multiphase flow simulation to using level set method, we also extended it to fluid structure interaction. And in our research group, most of the PhD students not only develop their in-house codes with some new improvements in the methodology. So then after developing, they apply to a certain problem, they generate big data, and they use data analytics to analyze the problem. So the title of my book says CFD Development Application Analysis. The training imparted in our lab involves all the three aspects of CFD.
Okay, thank you, Professor Sharma. Now I request Professor Somnath Roy to speak a few words about his research and experience with in-house codes. And
thanks, Professor Bose. So our group works on accelerated computing in fluid dynamics. We are more into GPU-based computations using our in-house code for thermofluids problems with moving and complex geometries. And the two methods we are using, one is image boundary method, in which you can have a Cartesian mesh in which you can model complex and moving geometries, and another method we are working on with the meshless method. Our focus is to look into large problems and how we can reduce, because GPUs have a limited memory size, how we can reduce the overall memory requirement for the code and port it into small number of GPUs and get a fast computing using that. And so primarily we're looking into biological flows. One of the aspects is biological flows, and of course some other biological flows include both arterial flows as well as flow over butterflies and other biological flyers. Also we're looking into some of the heat transfer applications, some high Reynolds number applications, because one of the idea is that how we can use GPUs for direct numerical simulation and go for, say, something like few 100 million cells or billion cell calculations.
All right. Okay, before we actually discuss the questions one by one, I'll just give a one-liner introduction to myself for the audience sake. So I'm an assistant professor of aerospace engineering in the University of Birmingham, and I have recently established my research group named Bio-Inspired Fluid Structure Interaction. So I'm a computational fluid dynamics engineer by training, but I do a little bit of experiments of low-speed aerodynamics. So, and in terms of computational fluid dynamics, I mostly use OpenFOAM extensively from my PhD days, and also now I'm using different version and my own development within the code of OpenFOAM. But I also have experience of developing an SARP interface image boundary method based code, code particularly for low Reynolds number flows. Right. So the way we will actually go about this panel discussion is that I have collected a few questions from our perspective, and I will ask the panelists and one by one, and we will hear to their perspectives on that. And as I said before, please feel free to write down your questions in the chat box if you have anything on that. So we thought the title of this discussion is open source code versus in-house code development and their impact in the CFD education industry and their applications overall. So my first question would be to the panelist, and we will go by first Professor Tabor, then Professor Sharma, and then Professor Roy in that order. So what do you think is the basically the difference between the training someone need to become an expert to write an in-house CFD code and become an expert understanding the logistics and the architecture of an open source code, and where can they start in their career to start with to use them, and what do you think about it? Professor Tabor, can you unmute yourself, please?
That's quite a question. I'm not quite sure where to start with that. Answering it most directly, and this may surprise you, but if I'm answering the question itself, where is the best way to learn how to write develop a CFD code? Undoubtedly, the answer is to go out and do it. So writing your own in-house code would undoubtedly be very beneficial. I'm sure Professor Sharma and Professor Roy have benefited personally from the effort being put into developing their individual codes. I think the advantage of using an open source code, in particular OpenFOAM, is, well, there are several. Writing a complete code from scratch is a lot of effort. I'm sure they will agree with me there. It's a huge task in its own right. The code will be local to the group writing it, so there will be a great deal of support and onboarding for new people to use it. And whereas with OpenFOAM or any other open source code, a lot of the effort is shared with other people. You have the access to the code, so you can go into it in detail and see how it works. So you do have the educational experience there, but you also have support amongst the community. There's CSF Naj's tutorial database. There is Håkan's collection of his MSc projects and things like that. I will say the other advantage, in my opinion, of using a common platform is that it gives us a common language to share what we do. If Professor Sharma comes up with a really great new CFD methodology in his code and Professor Roy wants to implement it, he has to read the paper and then work out how to put it into his code, which may be very different in its implementation. If Chandan comes up with something marvelous in CFD, which I want to use in OpenFOAM, I pick up the phone to him and say, would you mind sharing it with me? And hopefully he says yes, and I can copy it across and I can make use of it immediately. So we have a language for sharing what we do, and hopefully in both directions.
Thank you, Professor Tabor. Professor Sharma?
Yeah, so I strongly believe that before you start working on open source code, I completely agree with Professor Tabor that there you have a community, there you have a help which greatly helps you to progress fast in open source software code development methodologies. However, before you jump into this, you should have education or training into in-house code development to begin with. Especially, I strongly believe before you jump in front of computer and start doing things, it's extremely important that I commonly say that CFD is a subject which gives you an approximate solution, but each and every line has to be nothing less than exact. The program cannot be approximate. So and before you do actual programming, it's very important that you sit with pen and paper, plan things. I typically say that, like, to develop a hardware, you need to know what are the nuts and bolts and what is the sequence of connections which you used to make. Similarly, I say that in CFD code development, which I have emphasized in my book also, which is a unique feature, is implementation details. What will be the data structure? What will be the loops? So those details, those are nuts and bolts of in-house code or open source software development. So I believe that before you, OpenFOAM is an excellent platform in terms of community help, and but before you go into that, you should go through a journey of developing in-house code in the initial CFD training, which will greatly help you to go for open source. Yeah, so I have some other points which I'll come later on. Yeah, I'll leave it to Somnath then.
A year back, I was attending another panel discussion with OpenFOAM forum, and there are people from different application domains. Some of them, one of them made the comment that if we look into molecular dynamics, all groups use there are 2-3 open source softwares, and you go to any group, that group is using either of them. But if you go to computational fluid dynamics community, one group is probably using 2-3 different codes. So and there are few reasons behind that. I mean, there are different applications, even if we can think simply pressure-based and density-based codes. So same group is probably working in 2 different regimes and using 2 different codes. But more than that, it might be due to the legacy of training or something that sometimes we start believing that we'll only use this particular algorithm, this particular data structure for this application. And also it is that probably in CFD we have not that converged in terms of algorithms that we can put everything in the same framework, especially if we try to optimize one of the codes which is being used for some by bigger communities. It may be OpenFOAM, it may be JDs, it may be some other open source software. We sometimes find that probably our in-house code gives a better optimization compared to that specific problem we are using. So I don't think it's a versus problem, OpenFOAM versus open source versus in-house codes, but rather it's kind of a matter of choice based on the resources that are available with you and with the time which type of problem you are trying to solve. But yes, in terms of maintaining the repository, in terms of properly developing a software, community-based initiative like OpenFOAM is probably a mile ahead than all our small initiatives considering the legacy in-house codes. But I see that both will exist in their own capacity. The same group will probably use OpenFOAM as well as they will develop their own own codes. They will spend time on their own codes.
Thank you. I think we are actually hoping to have that optimized scenario where everybody will develop their own algorithm and try to integrate with open source softwares like OpenFOAM. I think it will take time, and we are approaching towards that. That's the positive thing. So I think I was thinking about a follow-up discussion on what do you think are the challenges in terms of open source CFD codes and the in-house code in terms of a student's learning curve. So when a new PhD scholar starts with, what do you think are the challenges in these 2 different type of frameworks? Professor Tabor?
Yes. Can I first of all absolutely agree with both of my panelists, but particularly what Professor Roy just said about it not being a choice. It's a question of the right tool for the right job here. So there's room for all of these solutions and commercial solutions as well. I teach CFD at Exeter using a combination of Fluent, which is a commercial code, and OpenFOAM, and I think it's valuable that students get a view on different ways of doing things so that it forces them to generalize their understanding. I don't think the majority of the people I teach are going to go off and write their own codes. What I'm looking for is that they understand how it works numerics and how to critically make use of whichever tool they end up using here. And I absolutely agree, a lot of that can come from writing code, solving problems, understanding the numerics, but doesn't have to involve reinventing too many wheels as we go along. Sorry, could you repeat? I'm sorry, Chandan, but could you repeat the question now? I think I've possibly got a little bit off topic.
Yes, actually, I was thinking to discuss the point that what do you think for a new beginner in CFD? What are the challenges in terms of learning curve of these two types of approaches? One learning the open source tools and one learning to write their own in-house code.
In terms of a really basic new user, let's say somebody, for example, joining Professor Sharma's group to use his code, I'm sure it'd be very similar to somebody trying to learn how to use OpenFOAM or something like that. There are the fundamentals of the CFD process. So it's a critical approach to what's going on, understanding the numerical and physical models and making sure they're the appropriate ones for what you're doing, validation and checking your solutions against known results, things like that. That's the core of what we need to do as CFD practitioners, basically. And that would be in terms of the use of any CFD code. In OpenFOAM terms, I tend to think of users of OpenFOAM. I have my own hierarchy of use of users who just want a CFD code to run problems and to answer questions, modelers who want to use the internal structure, the beautiful pseudo-mathematical structure to implement new models, and what I think of as gurus who want to fundamentally introduce new methods into the code, and things like solids for foam. And I think Phil Cardiff will be talking about that later. And I try and progress students up there. Obviously, to do that and to move from a user to a modeler, you need to know a fair amount about the internal workings of OpenFOAM and the way it's coded. And that will be very similar to any, I'm sure, to any onboarding for Professor Roy or Professor Sharma's code, learning the fundamental numerical methodologies and how these have been coded into whatever programming language they use. So a knowledge of coding in that particular language and how that's being used.
Professor Sharma?
Yeah, so I had numerous PhD students who had worked on in-house code development. Recently, I had a couple of students who had attempted to work on OpenFOAM. And I am answering your question based on the development perspective. Let us suppose we are trying to improve an existing method to improve the computational efficiency through open source platform versus in-house code. Then I'll come to the part 2 of this question, that once you have the code, if you want to apply to a problem using open source versus in-house code. Now, in the first part, when you want to develop or improve an existing methodology using OpenFOAM, I would say that OpenFOAM gives an excellent platform. However, there is always a struggle between the flexibilities which the student takes a lot of time to learn if he wants to develop certain things. But those are, I don't think, a major problem, which whatever I'm saying based on my limited experience with OpenFOAM. So OpenFOAM, I find, as far as developments are concerned, it's a very good. But in-house code development, I see that the time which is required, because each subroutine that you develop, you have to find up a test problem which may be even hypothetical. So it takes more time. But in both the types of training, the way I feel is that the student develop more confidence and, I would say, contentment more than anything, when he develops his in-house codes. So this was about the development part. Now, as far as the application part is concerned, when let us suppose you have an open house or in-house code and you want to apply to certain problem, changing the boundary conditions and then selecting the schemes, numerical schemes. OpenFOAM, I have found that my PhD students struggled because when I especially like a lot of data analysis. So I tell them to generate, I keep saying that we create movies, fluid dynamic movies. So through my student, I used to take a lot of data. So data extraction, especially the unsteady data, the flexibility in that in open source code versus if I give my in-house code, obviously I had found based on my limited experience that fetching data, especially temporal variations, that too, if you want some wall shear stress or all over the flow field, if you want to compute variables and extract the data with OpenFOAM, I found it's quite challenging. Whereas in open in-house codes, you have all the flexibilities and you can do it very easily. Chandan, you're muted.
Sorry, Professor Roy.
So there are a couple of aspects. One is that yes, OpenFOAM is very well documented. There are a lot of training materials available, and learning OpenFOAM is of course probably much easier if you can go through very well organized materials, and there are many helps. There is a very good forum for OpenFOAM also. On the other hand, there are some informal aspects in learning the in-house course because your lab seniors are using them and you probably see them whole day with making certain changes, doing something, and if you're working on a different problem but stuck somewhere, somebody who is working with the code for 5 years can readily jump in and help you. So these two are the aspects, but yes, if we think of making things formalized, if we think of saving man hours and moving in a more efficient way, of course OpenFOAM has a much smart learning curve. We cannot we need to admit that, and probably which is more important is that in case of in-house codes, if we can start learning some of the aspects from OpenFOAM, how to document it properly, how to make training materials for within our groups, or if we pass this code to someone else, how can he use it, that can be beneficial.
Yeah, I completely agree. Thanks all of you for sharing these insights, and I quite resonate with everything. So here, my view is that when I actually started using OpenFOAM as a code to learn, and I also did my CFD course writing, lead driven cavity flow, writing my own CFD code to solve that and to start with that. And basically, what I felt is that there was a lot of lack of documentation. Can you hear me or can you see my video?
We can hear you and see you, as I can anyway.
Okay, I think it was frozen for some time. Yeah, so that's what I was telling, like compared to that time, which is basically 2014 to today, there is a huge difference in terms of documentation, in terms of helps available in open source code like OpenFOAM. And I mean, the beauty of OpenFOAM, as Professor Sharma was saying, the difficulty of post-processing that we are overcoming through its integration with Python. I think it is a lifesaver if you can integrate your post-processing scripts with Python, and it is much easier to extract data from OpenFOAM. And of course, Professor Tabor can talk about runtime post-processing tools, and he has trainings of things in YouTube. And so basically, to sum up, there are a lot of materials available. But however, as I said, we all start with that benchmark problem, lead-driven cavity problem, where we try to understand the schemes by writing our own solver and then move on. So I quite resonate with that. But the problem that I I actually think what Professor Roy was mentioning is that about in-house code. We also have developed a sort of in-house code in my PhD days with my other colleagues who did PhD next, is to pass this code over generations and the documentation. So when we actually develop the code, we often neglect to comment it properly or to document it what particular scheme we are developing for that, which becomes an issue for the next researchers. So my next question is actually related to that. Like, for example, we are in this age of collaboration, we actually want to develop a solver for a very involved, complicated multiphysics problem, where basically a Navier-Stokes solver is the starting point. And then we can add complexities and add different capabilities. So what do you think? Can open source platforms or open source codes can play that role of the combination where we can take the Navier-Stokes solver, maybe incompressible, compressible solver from OpenFOAM, and it's an open source code. We can see the code, we can see all the schemes, and then we can add, for example, better fluid structure interaction coupling scheme, for example, better electromagnetic coupling scheme, or integrate different fields and different governing equation, write our own solver and solve it. What is your thought on that? Professor Tabor, I will start with you.
Certainly, the OpenFOAM approach would be fantastic. I've been reading through the chat itself, and there's been a comment where somebody's commented that OpenFOAM is very convenient for implementing certain types of modeling, and that's absolutely correct. It's built for implementing mathematical modeling and at the very top level, but introducing lower level changes can be quite challenging, and that's certainly true. Now, it's written in an object-oriented fashion, and one of the big advantages of that is the class structure hides implementation from the higher level users, and so it is technically very suitable for making low-level changes. In theory, I could rip out the whole of the solvers and replace them with new solvers, and you, Chandan, wouldn't notice the difference because I've changed the implementation but not the interface. However, I could possibly pull up the oxygen created documentation. The internal structure is very, very complicated, so that is not a job for the faint of heart. The main question here is verging on, I think, multiphysics, and of course that is a huge challenge. And how do we integrate a fluid dynamics solver with other solution routines? Now, at one level, all of these problems are continuum mechanics problems, so you could extend your own solver to cover the heat exchange of a neutron flux or the stress analysis. And that's, for example, something like solids for foam and some of the work being done on stress analysis in OpenFOAM and linking it in a monolithic case with the fluid solvers. But you can also adopt a heterogeneous approach where you build an interface layer which communicates between different codes. And that's how often commercial codes do it, but it's also things like in the open source scenario, Precise from the various German groups, MUI in the UK. I'm working with some guys in Australia who have developed their own in-house coupling between OpenFOAM and I think it's either lamps or lights for DM type things. And that does illustrate the strength of any open source code, but particularly given the background of support there is and the use of OpenFOAM, that is an obvious one for these developers to target. I'll pass over to other people now.
All right, Professor Sharma.
Yeah, so as far as multiphysics is concerned, many times the way I feel is that when you take other than the flow physics, if you take a physics corresponding to structural mechanics or acoustics, the transport mechanism or the numerical methodologies that you use, many times, as per my experience, I don't feel you can take help of the existing subroutines of OpenFOAM. So if you want to add additional physics, you have to develop almost entirely on its own. Although you can use the flow solvers and you can do the coupling. So yeah, so indeed, we are looking future with multiphysics problem. And of course, we can use OpenFOAM. And if we use this platform for multiphysics, it will help us to work together and have a better learning curve. So I think that's a good idea. But I understand and appreciate the comment by Professor Tabor and that people are doing it, and with OpenFOAM we can do it because it can give a better learning curve.
Mr. Roy?
I'll probably resonate 100% with my other panelists, and this is kind of a need of the hour that you solve multiphysics problems. As we are getting much better computational facility, we try to solve instead of using heuristics models, or even in terms of developing heuristics models, we need to solve multiphysics problems. But this is important that you need to call different solvers, port them into the right platforms, interact between the solvers. They're running at the heterogeneous computing environment. So this framework, and when we use with our own in-house code, we need to develop this framework, which is of course a difficult job considering our expertise also, because it needs computer experts in some cases to couple the software and see what are the right pathway of exchanging information and instruction between them, what should be the sequence of calls, how they will be mapped to different nodes of the cluster. But if I appreciate that OpenFOAM is thinking in that direction, that this framework will be built by and maintained by them, so that will be a great benefit for the entire community. You learn few of the scripts, you take the basic framework, and then couple the solvers, port it accordingly, use an efficient implementation.
All right. Thank you. So basically, I think I have a last topic to discuss due to the time, and then I will go through the chat box and take some of the questions that the audience has asked, and maybe some of the audience can also unmute themselves and ask the questions. So Professor Tabor, what do you think from the UK perspective? What is the current trend and the future outlook of the industry, and how the CFD industry or aeronautical or mechanical engineering industry, how are they looking upon these open source tools, and how is it competing to the commercial codes that is conventionally used in the industry?
Very good question. I do a lot of work with industry, and a lot of the projects are helping companies develop either a CFD capability or very often an OpenFOAM capability. And I approach this with new companies with a reasonably open mind. I'd rather they used OpenFOAM for a variety of reasons, but I'm happy to go with whatever seems to be the right solution for them. That can be a commercial solution, or as well as it could be an OpenFOAM solution. And in terms of the end use of the modeling, all of these codes that you can come up with have their benefits. They're all going to give good results if you use them intelligently and sensibly. The learning curve for using OpenFOAM can be more steep for a new user. I remember asking one of my students on my OpenFOAM course what she thought of OpenFOAM, and she said, I think it makes difficult things easy and easy things difficult, which I thought was a very accurate thing, and so there are going to be challenges with using OpenFOAM, and some companies prefer the security of paying for a code and getting more direct support as a result of that. But if you've got people who are good enough to use a CFD code to get the right answer, they are not going to have any problems with using OpenFOAM versus anything else. In terms of the use of CFD, it has grown massively since I was first introduced to it as a postdoctoral researcher. It's penetrated just about every industry you can imagine. It's probably easier to list industries which don't use CFD. And this is because everything we build or design or do either sits in air and or water and or uses some kind of a fluid as part of its operation. So there's going to be opportunities to use CFD. I've even done CFD with colleagues in archaeology, looking at the airflow through 9th century Indian iron furnaces, which is a great project, but not one which you might think of as being something to do in mechanical engineering. But CFD has a lot to offer across a wide range of industry applications and all sorts of areas such as biomechanics and so forth. And OpenFOAM can be a very, very good solution for a lot of companies.
Thank you, Professor Tabor. So now, Professor Sharma and Professor Roy, can you comment on the scenario in India? What do you think? How are the industries looking upon these open source frameworks? You are muted. Sorry.
Yeah, this is not my recent experience, but around 5 years ago, I was a CFD consultant for one of the company for around 5 years. So around that time, I had seen that the companies were not having the confidence. So they were indeed spending time and money to explore. And because the way I have seen is that the timelines of the industry and they don't have the patience of learning. And when say they have two choices, commercial software versus OpenFOAM, indeed they see that the timeline of the learning curve and getting things done are much faster. So based on that, I see that companies, whatever experience I had seen, is put OpenFOAM or an exploratory mode, and it has not been taken off, especially in Indian industry, as far as I know.
But do you think is due to the lack of the trained resources, or is just the output-oriented, sense of industry?
Yeah, setting up the problems and meshing and getting the data, there are the efforts. If you compare a commercial software versus OpenFOAM, and they don't have a patience. So that way, I find that it is taking more time. Yeah.
All right. Thank you. Professor Roy, do you have any comments on that?
Not exactly in Indian scenario, but when I was doing my PhD, I was working with some of the industries, more closely working with industries that time. And at that time, industries had their own in-house code. Industry in one particular domain has developed and legacy in-house code over 15-20 years, and they were using it. But I'm talking about 15 years back maybe, and that was the time when proprietary softwares were coming up heavily, and industries were in a process of stopping using their own code and moving towards proprietary software. The sole reason is that you need to maintain a small group probably, and there are a lot of support, a lot of solutions you can get from the proprietary software developers, their support groups. In India, what I realize, it's industry mostly, not only industry, even the research labs, they mostly depend on the proprietary software. But there are certain things that many times proprietary software, one is it's it is costly, but many times for defense or some other organization, it is difficult to use the proprietary software for certain applications, and sometimes they use their own code, but moving to open source can be a good solution for many. But point is that will they be able to get the right support which they get in terms of buying licenses from a proprietary software company? So that is probably one of the issue. But what is more important is, even in the academia, we see a trend is that institutes spend a lot of money in buying these licenses, and as you keep on increasing the problem size, you have to pay more licenses for more codes. And moving towards this open source is probably the best idea. You stop wasting money for license. Yes. But again, the point is that if you are not a hardcore computational group, you need support for that. And maybe there has to be a solution, a middle layer, that some support-based consultancies are coming up, which can help industries, if required, also academic groups, in terms of running this software efficiently. I think there is also a question that how can I say that this is most efficient implementation, etc. Because most of the application engineers are not from CS domain. So this is one of the very important issue, that there has to be a right support.
Sure.
That is probably stopping it.
I completely resonate. I mean, after I joined University of Birmingham, and I'm actually kind of teaching partly the CFD course and mostly aerodynamics, and developing a course on fluid structure interaction. So the current group of students, they learn ANSYS Fluent, and in University of Edinburgh, from my experience, they're completely based on star CCM. And so the university pays tons of money to buy the licenses. So I actually proposed to my head of school, and I told, like, I want to introduce open source softwares. And then I did some research, how much money the university is paying over these licenses. And I'm actually discussing on the higher administratives, and they suggest me to make a business case and propose to the University of Birmingham that if I teach my courses and all the other courses using OpenFOAM, how much money I can save from the university point of view, and can I get that as a project grant to run my research group or take some PhD students. So yeah, that's a side note.
Interesting.
If I can add to that, Chandan, as an academic, we often get very preferential rates from companies for the software. So our Fluent license is 10,000 a year for something like 256 licenses, whereas a commercial company might be paying double that for one license. So.
Yes. That's true. I mean, that's what my question was towards the industry and their choices. So, I mean, what I know that some of the startups and new CFD companies I have talked to and trying to establish my relationship, they're very keen. They're very keen on learning open source techniques to save a lot of money and make profit, more profit in their business. Yeah, so basically my last, I think Professor Tabor kindly has answered some of the questions, and I saw through the chat, I think most of the things we have already discussed, and we have 10 more minutes. So I'm very much eager to ask this question, which is more of a ethical question in terms of education, CFD education, and training the future researchers. So I see a trend, particularly because this platform is for OpenFOAM. I want to talk about it, that teaching OpenFOAM has become a business. So, and we have to agree at this point that I mean, things are changing now. More and more free training materials are available online. We get a lot of materials to learn ourselves. We can easily connect to experts like Professor Tabor. We can organize this symposium free of cost and spread the knowledge among the, let's say, 237 researchers who are listening to us. But particularly, this is more an issue in India, which I have noticed, and I have like kind of felt about it, that there are many small group of peoples or startups, or they're forming, and they're charging a hell lot of money just to teach how to solve Navier-Stokes equation using OpenFOAM, using simple form. And I just wanted to know, and because a lot of students are listening to us, from your views, what is your comment ethically on these kind of approaches, and where should we go forward? Professor Tabor.
Well, obviously everybody has to live. And you and I, Chandan, are lucky in that we are paid by our universities, our respective universities, to do particular teaching tasks. And other people may not be in that convenient position. An open source code, obviously it is being distributed for free, and people and companies need to monetize their use of it in various different ways in order to live, basically. One of the, I think, challenges with open source code development is making it work like that. If you're fluent, you have a revenue stream which you can invest in improving the code. It's less easy to do that with an open source code. In terms of learning the code, I have answered a few of these questions. I hope Professor Sharma and Roy would agree with at least what I've written. You can add some other things yourself. I always point my students to Joseph Naj's material, which is very well written. He curates the governance tutorial wiki. Yes. He also has his own YouTube channel. He also, I believe, has a Patreon channel, which of course is a commercial service which he gets money for. He is very, very good. He knows his material. I guess where it becomes more challenging is when you might have people who are charging for less beneficial, less well-written stuff. Sometimes our students ask me, why are we paying 9,000 a year for you to tell us to watch YouTube videos? And I tell them, you're not paying 9,000 a year for me to tell you to watch these videos. You're paying 9,000 a year for me to tell you what videos to watch, and there's a difference there. You have to hope that over time, those people who are providing genuine value for whatever they're charging will survive and will make their living out of that. And if there are people who are failing to provide value for money, people will realize that and move away from paying that money. So, that would be my attitude.
Sure, fair enough. Professor Sharma.
Yeah, so the way I see it is, especially as you had said in Indian context, that there are a lot of companies who are taking a lot of money for training. So it all depends on the job market scenarios, as I indicated, that a lot of companies are exploring. So they are looking for the job market where they want to hire trained manpower in OpenFOAM. So especially I think you can resonate with me that the job market drives ultimately to the students. And many times in academia, we are not doing, because especially in Indian academia, we believe strongly that teaching how to develop your in-house code, I keep giving example, we teach how to make a car than how to run a car. So we do not teach you how to run a software, but how to make a software. So in academia, maybe we are not into those business. But there is a job market, so it is leading to this case. Yeah.
Sure. Thank you, Professor Roy.
I'd rather say that through this NSM National Supercomputing Mission project, we are trying to address this gap. There have been few tutorials developed in OpenFOAM. We have made some video resources. Even through this symposium, we'll make some video resources. So there are big commercial initiatives. Of course, it will be. If it has a market, people, of course, will try to leverage it. That there is nothing bad in that. But also from government spending, we are trying to the government-funded projects. We are also trying to develop some of these initiatives.
Thank you. I think, I think I just wanted to point this discussion out so that, of course, the students will make their own choices, but they can hear from the experts what is the perspective. So I think we are almost towards the end of it. And in the chat, I don't see any new questions, which there are some questions which is specific to GPU, and I think the discussion can happen, but related to the discussion we had in the panel, I don't see anything. Professor Roy, you can point out if I'm missing something.
Some of the questions I have answered, and I think Professor Gavin has also answered some questions in chat. So there is one question regarding validation. Whatever you do, any small change needs a validation, and you just wrote about validation. This is the first thing in CFD.
I think this reminds me of this no model is correct. So we are ultimately modeling things. So we need some error estimation and uncertainty quantification.
There is a question on free resources to learn OpenFOAM. Probably share OpenFOAM.
Yes, I will share a link. I think the OpenFOAM tutorial wiki is a great place to start with. So as Joseph, I'm seeing he has put a lot of effort, and with other committee members, and I'm privileged to be within the committee, and I tried to contribute a little to that. So basically, there are a great resource in the wiki page of OpenFOAM tutorial. I'll share the link in the chat. That is a great place to start with 3 weeks training, glimpses of tutorial, etc., and contributor specific tutorials. I will share the link in chat. So I think I am really glad that this discussion took place here, and would actually trigger some thought process among the audience who are present here. And I actually sincerely thank all our 3 panelists to actually put their thoughts on these questions. And we had a different but very much synergizing, thought process in the whole set of questions. So if the audience doesn't have any particular question related to this panel discussion, I would close the session. If you have, please raise your hand. We can unmute yourself and you can ask the questions. But please ask relevant questions to this panel discussion. Right. So if not, let's thank the panelists again from on behalf of all the audience and me. Thank you very much, all of you.
Thank
you. Thanks for the opportunity.
Yes, please.
It's been a great pleasure.
Thank you. Thank you. So let's close this session, and we have a 10 minutes break after this, and then we will continue.
Someone has raised a hand.
All right. Can you please unmute? Oh, Thor has. Okay.
Just 1 minute. Yes, you can probably unmute yourself.
Thor, can you ask your question, please? Oh, so I think he has done it by mistakes. No worries. Thor is one of our trainer tomorrow, so we are looking forward to his training. All right. Thank you very much, everyone. So we meet again after 10 minutes of break. Thank you very much.
Thank you all.
Thanks, Chandan. Thanks, Dr.